Okay, so we've covered how to integrate ordinary differential equations in the past. We will cover a different way of doing the same thing using multi-step methods. These are more accurate than the single-step methods we talked about. What do we call the single-step versus multi-step? In single-step methods, like the one we discussed before, we just use the data of at a particular point in order to advance the calculation. So for example, to compute yi plus 1, we used f of xi yi. These methods use information from not only at the current step but also at the previous step, and sometimes they also want predictions from a future step. So these methods are called multi-step methods, and it will be obvious once I write down the equations. They look something like this. So there are two types of methods we'll talk about. One are the implicit and the other are the explicit methods. Let's just do them one at a time. So multi-step method is what we're going to cover today. Okay, and they call so because they need information at multiple time steps. Okay, so one class of methods is they actually had some formulas which we'll basically use. They are the Adam Bashforth method. This is an explicit method, and it'll be obvious what explicit means in just a bit. So the best way to understand this is through the formula. Yi plus 1 is yi plus delta x. Okay, so now we have 3 divided by 2 f of xi yi minus half of f of xi minus 1 yi minus 1. And then I'll also put the truncation error here. The truncation error is of the order of delta x cube. So it's accurate to second order. This one, okay, has a name. It's called Adam Bashforth second order. I'll tell you why it's second order. It's also known as the Adams second open formula. Okay, everything will become clear in just a bit. Let me just continue writing this for another variant of this, which is more accurate. It actually uses more than one values of f. So more than 2 values of f. So 23rd divided by 12 f of xi yi minus 16 divided by 12. Okay, there's a reason why I don't simplify the 16 by 12. Again, it will be obvious in just a bit. Xi minus 1 yi minus 1 plus 5 divided by 12 f of xi minus 2 yi minus 2. Okay, need some space for the truncation. Okay, and the truncation is of the order x raised to 4. This one is known as the Adam Bashforth third order, or Adam's third open formula. Third open. Okay, I'll explain all this with in just a bit. Generalized Adam Bashforth method. So the formula is I plus delta x summation m goes from 1 all the way to n. What's n? And m beta and m f of I plus 1 minus m plus the truncation is 1. Okay, so what is f? The f here is I plus 1 minus m is the same as f of x I plus 1 minus m y I plus 1 minus m. Okay, so all the formulas. So this table you'll get this once I post this, but let's go back a little bit and then see what this is. So as I said, this is a multi-step method. Now, multi-step method, you use not only information at the current time step, but you also use them in the previous time step or the future time step. So this one is known as the second order formula for a very specific reason. You use two values of f. You use the value at xi and the value at xi minus 1, xi minus y minus 1. So that's why it's called second open formula, and it's called second order because the truncation error is delta x cubed. Okay, so we've only seen methods which not use only current time step. This one is known as the third order formula because the error here is delta x raised to 4, but then it's called third open formula because I believe it uses 1, 2, and 3 values. So it needs the value at the current time, current step, xi, yi, previous time, and the one before that. Now these formulas, as you see, get better and better. So it's more accurate as you increase the number of function evaluations. So 2 function evaluations give you delta x cubed, 3 function evaluations gives you delta x raised to 4. So you could actually keep going. So this table here gives you a more generalized formula. Well, coefficient of the formula. This is what the equation looks like. It follows the theme of the previous equations. Just generalize it with beta. How do you compute this beta? This beta is in this table. Okay, so here is beta. Maybe here that's beta. And then this is for different orders. So for example, if you were to find what is the Adams second order method, it's buried here. So we see that this is the second order method. I have coefficient of 3 and minus 1. So actually 3 and minus 1, right? You can see the same thing over here. This is second order. This is a 3 and there's minus 1. Remember, this is twice beta. So you need to put half here, right? So that's how you get that. Now, if you want to confirm the value of the third order formula, so you can see there's a 23 minus 16 and 5. Just go back here and see it's 23 minus 16.5, and then this 12 has to be the denominator that's basically sitting right here. Okay, and that's why I wrote it 16 divided by 12, because I want to pull that 12 out the way they have done it here. So you could do first, second, third, fourth, so on, and as you do higher and higher order, it becomes more and more accurate. Okay, now it's best illustrated through an example. So let's see how to use this method in a problem. Okay, so here is the problem example. So here's the ODE. It's dy dx, which is the same as f of x comma y equals x minus y. Use Adam Bashforth method of order 2 with a step size of delta x equals 0.1 to compute the solution for, so we'll go all the way from x0 to 0.5, and the piece which is missing here is I need to give you the initial conditions. So let me just specify it right here. It's the ODE. And the initial condition which is required. So it's a first order ODE. So I need to give you one initial condition. It is y x of 0 is 1. Okay, so we know how to do this using Euler's method, Yoon's method, and so on. They actually will use the value of f at that point. So it will take, so all these methods we've seen so far will take the value at x equals 0 and find the value at 0.1, then use the value at 0.1 to find the value at 0.2, and so on. Let's try to use it with the Adam Bashforth formula. Let me just write it down. Adam Bashforth second order. Okay, so the formula is yi plus 1 is yi plus delta x 3 divided by 2. I'll just use a shorthand. I'll just call this fi minus half fi minus 1. That's just to indicate it's xi and xi minus 1 for the second one. Okay, we got this. Let me just put a note here. This is simply f of xi yi. This is f of xi minus 1 yi minus 1. Okay, so here's what we'll do. We will compute the solution at xi equals 0. Well, we know what the value at 0 is, 0 0.1, 0 0.2, 0 0.3, 0 0.4, and 0 0.5. So let's try y of 1. So put I equals 0, we get y1 equals y0 plus delta x 3 divided by 2 f0 minus half f minus 1. Okay, so what is minus 1? It's basically the value of x at minus 1, or in this case, if you're looking at 0, the value which will come before this would be minus 0.1. So we want the value at minus 0.1. That value should go in the f. F is basically this. So the thing is, we do not have, the domain is basically 0 and 0 to 0.5. We don't know value at minus 0.1. Think of x as time. If you have x is time, time starts at 0. There's nothing defined at time equals minus 0.1, of course, unless you have some experiments running before that. So this is not going to work. This is just not possible. You cannot use this formula because of this. This is the issue. The data not okay, so you can't do that. Okay, so in fact, as you'll see, uh, if you had the value, well, you can't use this formula, so there's no way you can get y1 from this. But if you want to do y2, I'm just going to put I equals 1 now, delta x 3 by divided by 2 f1 minus half f0, then it turns out I can actually compute this because assuming that I know y1, I'll know this. Assuming I know again y1, x1, I'll know this, and I'll know this, right? Because that's given to me. So this will work. I can compute y2, but I cannot compute y1 using this formula. So this is the deal with these methods. These are not self-starting methods. They cannot start giving you the solution because the solution at -1 is not available. So what you have to do here is you need to find what is the value at which it can be used. So if at I equals 2, it can be used because we have access to, we could have potentially have access to 1 and 0, and then find the solution for f of 1 or y1 using another methods, one of those single step methods like Euler's method, Runge-Kutta, Hume's method, doesn't really matter. Depending on the accuracy you desire, use another method. So what we'll do here is we will use, I'll put a note here. Use single step method, e.g. Euler, to compute this. So once we make that computation of y1, we can compute y2 using Adam Bashforth. We can compute y3 and so on. So let's do that. So we'll first use Euler's method. You can use any one. In this case, we'll just use Euler's, but you could use Runge-Kutta if you care about the accuracy. So what we'll do is we'll use Euler's method. Use Euler's method to compute y1. So y1 equals y0 plus Euler method is delta x f of I or f of 0. So y0, our initial condition was given to us as x equals 0, y is 1. So this is 1. This, by the way, is equal to x minus y. So I can write delta x is 0.1. So x minus y, x is 0, y is 1. So this comes out to be 0.99. It's 0.9, sorry. Now use Adam Bashforth for I is greater than or equal to 1. So now we can say y2 is y1 plus delta x, and I'll write the formula 3 divided by 2 f of I minus half f of I minus 1. So I is equal to 1 in this case, so this will be 0. y1 plus delta x, I'll just substitute, makes it easier. x1 minus y1 minus half x0 minus y0. Okay, so we know what the value of y1 is 0.9, delta x is 0.1, 3 divided by 2, x1 is 0.1, y1 is 0.9, half x0 is 0, y0 is 1. So y2 comes out to be 0.83. Okay, so you can check this. So you can keep doing this. Now you, for I equals 3, do the same thing, use Adam Bashforth. So let me just write down the answers I get. So I did this offline and I give you the solution, and I would recommend that you try to apply this for 0.2, 0.3, and so on. So this is what I got. It's always good to illustrate this with a table: xi, yi, yi plus 1. Okay, so we use Euler, and this is the solution we got here. This is exactly this part, 0.9. Okay, that's one, and I use Euler's for that. So I wrote that down. Next, for 0.1, we obtained this value, 0.83. So that goes next. So always carry this over here, then 0.83. So this will be, I'll call it Adam Bashforth. Then for 0.2, again carry this down. This is a calculation which I am not doing in the class, but you should do it at home. If you use the Adam Bashforth, you get 0.7755, then 0.3, 0.7755, 0.7357, 0.4, 0.7357, 0.7091. And I use the same method, Adam Bashforth, all over again. Okay, and then if you want to read out the final answer should sit in this table, in this particular column. These are the 5 values we're after. Solution.